17. Number 17 is actually a break. It's easier than those other two. It's okay. So we have NO2 yields N2O4. This one's kind of weird, but it's not hard. Set up your ice table, and then you'll look at me and say, oh yeah, that's weird.
And then, oh yeah, it's easy, right?
Hope so.
Or maybe it's easy for me. Well, don't.
Everything's easy. Disappointed.
Precisely. It's Mr.
Wait.
I thought it was gonna be one of those like one-to-one, yes, but you know, whatever.
So we have a case where this is not 1-to-1, it's 2-to-1.
Sad, crying.
Sad.
Oh, this is weird.
Wait.
You're so weird. What's the active item?
Yes?
Wait, so we're gonna have quizzes for each chapter and then giant test and equilibrium, right? Okay.
Yep.
Wait,
I mentioned this problem was kind of weird. What's weird about it? Yeah, all we're starting with is the products of the reaction. It's got to shift to the left to make reactants.
So you,
And you say, well, why don't you just turn the reaction around? Well, that would invert the K,
yeah, let's-
right? You remember when you turn a reaction around, it misses K. It doesn't miss. I mean, you could invert it again. But you can go ahead and just assume that it shifts left. That means what's going to happen to the 0.125?
Yeah.
It's going to go down. Now, we know what it goes down to. So do you know the X value, how much it changes by?
Yeah.
It went down from that to that. That's a change of 0.05. A downward change. It's a negative change.
Yeah.
So what happened to the concentration of NO2?
One up by 0.2.
By how much?
0.0.
2 times that much.
2 times? Well, that's 2-to-1 ratio.
See that?
Yeah.
So however much the N2O4 goes down, that much is how much the NO2 goes up. So plus 2 times that much, which is 0.1. And so therefore this measurement is 0.10 molar at equilibrium. Not this time. The question is, what is K? Oh, well, we got this. K equals 0.075 over 0.1 squared. Don't forget to square it. Concentration to the power of the coefficient. And I believe K is going to be 7.5. 0.1 squared is 0.01. Divided into 0.075 gives us 7.5.
Can I have something really, really dumb?
Okay, I got a question for you. Yes, Lena?
Where are the units?
No units on K ever. I always try to put a box where the question is asking, okay, the question here was, what is the concentration of SO3 at equilibrium? So I put a box there to know, okay, when I solve for X, that is my answer. That kind of thing. And over here, that was what we were trying to find. And so just stay organized like that, yeah.
Well, like, how do you know what to put? Like, for PCl5 and C, how do you know it's negative X? How do you know it's 2.5?
Oh, because you know that when you start with some amount of reactants and there's no products at all, it's got to go to the right. Since it's got to go to the right, this number's got to go down. And these will have to go up. When you start with 0 of something on the side, it's got to make it. Because remember, equilibrium means that there's some products and there's some reactants. So if you have 0 of something, the reaction will make it.
So the negative X doesn't necessarily mean negative X, it's just minus.
Yeah, it's going down by some amount X.
Okay.
Right. From 2.74, it goes down by that amount. Okay? All right. How we doing for time? 11:16. Got a toughie for you.
No. Is it
They were
18?
tough.
I'm gonna walk through it with you.
They were tough. Oh, wow.
Let's look at this one.
What? Wait, what?
Yeah, let's try number 18. Look at number 18 of the handout.
It's not true. It's not true.
Are you writing on the handout? Yeah, right at the bottom of the page.
All right. No.
All right, so 18 is just, it's a whole paragraph of information. In an equilibrium mixture of these gases, the partial pressures are given. And I had gone ahead and put those up on my ice table. So that first equilibrium mixture is not a big deal. You're just going to put what the pressure of each substance is underneath its symbol. But then the change. Something happens to this equilibrium. What is it? More H2O is added. It doesn't say how much more, it just says that more is added. And then what happens to the reaction when more of one of the products? Doesn't that throw the program off? That throws the whole thing off. When you add more of something, the reaction is at equilibrium. That means it's just sitting there. Now we've added some of one of the products. That throws that balance off. So it's going to go back to the left. That's Le Chatelier's principle. We learned about that in Chem 1. We'll talk more about Le Chatelier's principle. But the point is, it goes back. Now, if you didn't know anything about Le Chatelier's principle, keep reading. It says more water is injected. So this is added until the equilibrium pressure of H2, this thing, becomes 10. So you know that the H2 goes up to 10, right? So that means the reactants went up. That had to cause the reaction to shift back that way. I guess it didn't cause, but as a result of adding more water, the reaction went that way so that the H2's pressure went up to 10. Here's how I'm going to organize this. More water was added. I don't know how much more. I'm going to call it plus X. What else do we know? Huh?
Like if you add more water, that means that like the ATM of that or that will like go up. Not
Yes.
the H2. Or are
This gets thrown higher. It's higher now. The reaction is going to shift back that way.
they're going to go.
Yep.
Thanks.
So the H2 is going to wind up at 10. The problem tells us that. I should have done the same color, I guess. Oh, well.
Just under red.
All right, so if we know the initial pressure of H2 and the final pressure of H2, do we know how much it changed by?
.75.
So we know how much is shifted to the left. It's shifted by 3.75 atmospheres. Do you agree with that? This and this were given to us, so we can figure out what the change was. If this went up by 3.75 atmospheres, what did this have to do? It had to go up by the same amount. They're producing a 1-to-1 ratio when it shifts back this. You can't make this without making that. But K doesn't change as long as the temperature's the same. Hang in there. Just watch. So I know that this went up by 3.75. And so its equilibrium pressure is 9.50. Yes?
So if they're all in 1-to-1 ratio, then why are we like subtract or adding like 3.75 to the product?
We're going to. Because if this went up by 3.75 when it shifted this way, what had to happen to the CO? It had to go down by 3.75. That's right. So this is a minus 3.75. Now for the water, some water was added to cause this whole thing to shift. I don't know how much water was added, but I just know that everything shifted that way and went and changed by 3.75 atmospheres. Do you think the water had to get used in that shift?
Yeah.
How much water?
3.7.
3.75 atmospheres. So some amount of water was added to cause this thing to shift by 3.75 going the other way. So that means that the CO's final equilibrium pressure was that minus that, which is 10.13. And what about the water? The water is 5.18 plus X minus 3.75. And you're going to be stuck with some X term in there. Let's just write it down. That minus that is 1.43 plus X. What do we do with that now? We don't have a K value to put the products over the reactant. We don't know what K equals. Maple?
But use K from the first one.
You got it. This thing right here, the problem told us this was an equilibrium mixture.
Oh.
So you can find the K value, which Vinit does not change, down here.
I had a question about that though.
Yes.
Like, so, can you actually just take ATMs and just like shift them over? Like, would that be legal?
What happens was probably a needle was taken with water vapor and injected into this whole mix. This whole reaction vessel has these four things all in it at a certain ratio of products to reactants. So a needle is taken and more steam is added in there. That causes more water to react with CO and go back this way and make more of these things.
So,
Nabil, yeah, I can hear it. You can see it.
Here we go. Oh my God. You wanna go?
Oh, what a gracious audience! They clapped. No, I'm only kidding. Don't.
Thanks.
I'm only kidding. I don't want you to. I don't expect you to want you to.
You have notifications. They're too formal.
Not for showing me applause. I don't need that. So anyway, stop, because it's almost time to. Oh gosh, very almost time to leave. So find the K from this, and what I was talking about there before Mr. Hevel rudely interrupted was that the reaction shifts back this way because of the added H2O. Anytime you add more of a product, even if it's only one of the products, the reaction is going to shift back and make more reactants. To try to keep that K value, the K's got to be that ratio of products to reactants has got to be the same. So now, what happens is Q has been made greater than K, so it shifts back this way until Q equals K. So go ahead and finish the problem. Mabel?
so we're finding 1.43 plus X, right? Not just X.
Yes. Well, the question is what? What is the equilibrium concentration? I didn't write that down. For 18.
So yeah, you would.
Or yeah. This thing right here. I need a box around this. That's what we're trying to find. So find X and then add it to 1.43. Yep. Yep. So you're going to use the initial amounts to get what that value of Kp is. That times that over that times that is Kp. Then take that same Kp and that times that over that times that. K. Good one. All right, it's 11:25. My friends that are watching on YouTube, we're going to stop there. I don't remember what the answer is. Anybody have the answer?
We didn't get it.
Come on. Christina? E. You got E? Do we trust Christina?
Yeah.
Trust Christina because you know.
Christina's got E. Will you put the camera on her so they know which Christina we're talking about? Yeah, we know that. We'll say hi. All right, gang. We're out. Thank you.